Now the previous theorem makes us understand on whether we can approach the similar sort of a theorem in the reverse process. Given a rational number, can I express it in decimal form? Or given a rational number, can I identify whether that can be expressed in the terminating decimal form? So is how we understand the same theorem going in the reverse process. And it is very important because understanding the concept in the forward and backward process is more important in mathematics. So let's see with a couple of examples on rational numbers and then see if the decimals are terminating. So as I've taken in the previous theorem, clearly if the decimal is terminating, then its rational form will have the denominator q in the form 2 power n into 5 power m. So similarly, if my rational number has its denominator in the form 2 power n into 5 power m, then I understand that when I simplify that to a decimal, the decimal is terminating. It's quite simple. So let's see with an example. Converting rational number to decimal form. So when I want to convert, let's take one of the example problem, 25 over 2. Now clearly this is a rational number in its most simplified form where p is 25 and q is 2. So before we proceed to understand whether the decimal would be a terminating decimal or a non-terminating decimal, then in this case I identify firstly the value of q. Now here p is 25 and q is 2. Now q is 2, which can be clearly expressed as 2 power 1 into 5 power 0. Therefore clearly this being expressed in the form of 2 power n into 5 power m. So therefore, because of this reason, 25 by 2 in its decimal form will terminate. It is not a repeating decimal, but it will terminate. So as you can see in this, let's see how, to what value does it terminate. It's quite simple, because when I want to just find the decimal value of this, I simply divide, because we know the division process through which we can find 25 over 2. Taken in this form, 2 12s, 24, 1 0, 5 and 10. 0 is the remainder. Therefore 25 over 2 is 12.5 is how I do it through the division process. There's another process through which I can find the same fraction converted to the decimal. So let's see how I can do that. So for example, I take the same problem, 25 over 2. Now, I always try to make the denominator as 10. So when you have the denominator as products of 2's and 5's, then making the denominator as 10 is the most urgent need in case of those problems. So for example of this, when I take 25 over 2, I can write this as 25 over 2 multiplied with 5 and divided with 5. The reason being that when I multiply 2 with 5 in the denominator, I get 10. My target is to make the denominator as powers of 10. Therefore, I can do that when I multiply 5 to the denominator and equally multiply to the numerator, so that I get this as 25 times of 25 is 125 and 2 times of 5 is 10, and this would give me 12.5 as the answer. Is the other way of doing the decimal value is with alternative method. So this is the alternative method through which you can find the decimal. Let's take another example. Now I have 7 over 80, where in this case P is 7 and Q is 80. Now my first target is to see if Q can be expressed in the form 2 power n into 5 power m, as in case of this. So let's see how we can do that. So when I take the factors of 80, 2 40s, 2 20s, 2 10s and 2 5s, as I can clearly see that 80 can be expressed as 4 multiples of 2 and 1 multiple of 5. So that 80 can be written as 2 power 4 into 5 power 1. So that clearly this is in the form of 2 power n into 5 power m, where n is 4 and m is 1. M is 4 and n is 1. So this is how I clearly understand that because I can express q in the form 2 power n into 5 power m, therefore the given rational number can be expressed as a terminating decimal. The most important concept supported by the theorem. So let's see what is that terminating decimal value. So in this case, if I go by the alternative method as I proceeded here, similarly I take the rational form 7 over 80, and because 80 can be expressed as 2 power 4 into 5 power 1, then clearly I understand that this, when multiplied with this, can be expressed as powers of 10 if I can make the powers of 2 and 5 to be same. Remember, we need to make the powers of 2 and 5 to be same, and then only I can express the denominators as powers of 10. So as my power of 2 is 4, my power of 5 is 1, I need 3 5s to make this power as 4, thus balancing with the power of 2. Therefore, simply what I do is I multiply with 5 cube and divide with 5 cube, so that when I multiply 5 cube with 5 power 1 by the first law of index, I get 5 power 1 plus 3, which is 5 power 4, and then the powers are same. So that is my target out here. So in this case, this will be 7 times of 5 cube by 2 power 4 into 5 power 1 plus 3, which is 4. So my target out here is reached because I have made both the powers of 2 and 5 to be same. And I made them same by multiplying with 5 cube and dividing with 5 cube equally. Therefore, this would give me 7 times 5 cube is 5 5s 25, 25 5s 125 by 2 power 4 into 5 power 4 by using the law of index a power m into a power n, a power m into b power m is ab whole power m. Therefore, I get this as 2 times of 5 whole power 4. So this is how I get, by using the law of index, 2 times of 5 whole power 4. The next step is I multiply this so that I get 7 5s 35, 7 2s 14, 7 1 7 8 by 10 power 4. So 875 over 10 power 4 is what I get when simplified, because 2 5s 10 power 4. Now as I understand that the denominator is with 10 raised to 4, I have my decimals moving from here 4 steps to the left. So I have this moving 1, 2, 3 and 1 0 added and to the 4th step. Therefore, the answer for 7 over 80 in its terminating decimal form would be 0.0875. The terminating decimal of this, as obtained through the alternative method, is how we get this way. Finding q, identifying q to have in powers of 2 and 5 is the first step through which I understand the concept. So this is how I get the concept of terminating decimal and non-terminating decimal. Now, with this example, we support finally with understanding of rational numbers and decimal values of the respective rational numbers as compared to each other. So let's take an example problem where the decimal is non-terminating. So for example, I take so in this case 5 over 18 is clearly understood with p as 5 and q as 18, and immediately I want to express this as powers of 2 and 5. So let's see if I can convert this. So when I take this in the form, 18 can be written as 3 6, 3 2s. So 18 can be written as 2 power 1 into 3 power 2. So, but clearly I understand here that the primes here are 2 and 3, but for terminating decimal values, I need to have P and Q, which can be expressed in the form 2 power m into 5 power n. But clearly I see that this cannot be expressed in the form 2 power n into 5 power m, because there's no phi here. So this makes me clearly understand that therefore 5 over 18 cannot be expressed as a terminating decimal. It cannot be expressed as a terminating decimal value because it keeps on repeating. So let's see how it cannot be expressed as a terminating decimal value, supporting the statement out here. So randomly I divide this 5 over 18 as 0 taken with decimal 18 twos, 36, 40, 14, 140, and 140 when taken 8, 18 threes, 18 fives, so 7 times is 126, and then 14 again 7, 126, and 14 again 0, 7 times 126, and so on and so forth, and so on and so forth. Therefore this is not a terminating decimal. It keeps on repeating and repeating. Therefore I get 5 over 18 as 0.27 bar. The bar indicates it goes on repeating and repeating, never ends, as supported with the division here. So this is how we get the values in decimal form when it is not